You guys wanted me to talk about eigenvectors, so let's do this. Every matrix is really a transformation of vectors. For instance, these three vectors get sent over here, and you'll notice that that orange vector gets sent down, but that blue vector gets sent that way. You might wonder if there's some vector in the middle that doesn't get rotated at all. This pink direction here does not get rotated by this matrix, but it does get stretched by a factor of about 1.3. There's also a green vector with the same property, but notice it gets stretched a lot more. These vectors are called eigenvectors, and they're really important in math. We also usually keep track of the stretch factor, which I think is about 1.38. Maybe 3.6 over here, and this is what's called an eigenvalue. That's representing the scaling of those vectors. At the end of the video, I'll show you how this parabola helped me figure out those stretch factors, but first I want to show you some application. Our original matrix was written with respect to the left, right, up, down coordinate system, and those directions both rotated, and we had to keep track of 4 numbers in this matrix to encode everything. But we don't have to use that coordinate system. What if we used a coordinate system of eigenvectors? Then we would only have to keep track in our matrix the 2 stretch factors. So instead of 4 numbers, we'd only have 2. That might not seem like much, but what if we had a 100 by 100 matrix? Well, then instead of keeping track of 10,000 numbers, we'd only have to keep track of 100. This is a starting point for lots of algorithms for like data compression. This type of matrix is called a diagonal matrix, and if you take any power of it, which corresponds to iterating the transformation over and over again, it's very easy to predict. You're just going to get powers of those numbers. This can be really useful if you're studying like long-term behavior, what's going to happen 5, 10 generations down the line. I don't have time in this video, but there's actually a beautiful story that starts with this matrix and goes through these pictures and actually ends up with the Fibonacci numbers. And with the help of eigenvectors, you actually get formulas like this for Fibonacci numbers. It's so cool. Okay, but I promised to talk about this parabola. What's going on? If I'm looking for an eigenvector of this matrix, I'm looking for some vector xy, so that if I multiply by it, I just get a multiple back. This is really a system of equations, and if I write that out and move all the x's and y's to one side, I get exactly this. I'm going to rewrite this as a matrix equation. My eigenvector, whatever it is, has to satisfy this equation. But notice that this vector gets sent to 0, 0. So this new matrix over here has to have determinant 0. That's the only way a square matrix can send a non-zero vector to the origin. That must mean my scaling factor has to satisfy this equation. So I just typed that into Desmos to see what the graph looked like, and I found the 2 solutions. I could use the quadratic formula too, but I love graphs whenever we can use them. This shows that there are 2 possible scaling factors of 1.3 and about 3.6. We could then take those and plug this back into the system and then figure out what the vectors x and y had to be for each of those values of lambda. This is all stuff you would learn in a course called linear algebra. Thanks for watching.